Hello and welcome to the video. Welcome to another video on the channel. My name is Williams, and in this particular video what I want to do is to go through a little bit of a primer regarding programming 3D graphics using C#, and in this particular case we're going to be utilizing Viewport 3D, the Viewport 3D namespace, in order to visualize some of these 3D graphical rendering techniques. So this will be the first in a series that I'm planning on doing, and I'm going to go into certain branches of the theory and some practical examples regarding vertexes, indexes, index arrays, cameras, and all the other kind of semantics that goes behind generating 3D graphics. As per this channel, generally sort of covers 3D and 2D graphics with regards to video games. So I thought this might be quite a nice sort of a lead up from my last video on Viewport 3D, where I went through a little bit of a demonstration on how to do texture mapping using the namespace Viewport 3D namespace rather. And I also made a previous video as to how to generate 3D graphics with Viewport 3D as well. So I have two Viewport 3D videos on the channel at least. This will be the first in a new series. So without much further ado, let's get straight into this video. So the first thing I want to do is draw your attention to what's going on here in my view here, in my Visual Studio session. I'm going to go through some of the properties that are utilized here in the XAML. We're going to start off by working in the XAML first and foremost, because it's the simplest way to script the very simple and quick 3D graphics without having to worry about too much of the functionality and the setup with regards to forming 3D geometry, programmatically. We can just script everything in the XAML side, and it will be quite sufficient for the needs that we need right now. So without much further ado, let's get straight into this. So I'm going to go down, and first thing I would actually mention is that you want to have a grid containing all your viewport information, because a grid is probably the best way using the WPF front end, or even if you happen to use even UWP, which I don't believe the Viewport 3D namespace is supported in UWP, but grids are probably sort of the main container base that you will need for any kind of control you're using here. So in any case, I have Viewport 3D. Now, what is the Viewport 3D namespace? So this is the main class for containing 3D graphical information. This is needed at the top of the XAML, or rather the hierarchical structure of your scene. So I'd recommend the Viewport 3D namespace within a grid control. Just makes things a little bit easier. Now, you can see that I've given it a simple name, Viewport 2. It's got a margin definition here, so it's positioned on the screen. If I actually just zoom out quickly, if I can just go to the designer view, you see this is just like an empty space. And I have one single piece of geometry, which is a cube, and I've given it a crate texture. So it has kind of a nice crate texture and a bit of lighting to kind of add a little bit of the dynamicness of, it kind of sells the scene just a little bit more than just kind of a monolith texture. Anyway, going down, we have a camera. Excuse me. So a camera, what do we need a camera for? Well, a camera is a component that allows us to view the 2D, 3D information within the viewport. There are different kinds of camera, namely perspective camera and the orthographic camera. Now I'm going to leave some links in the description of this video with some great references, third-party and official MSDN references to 3D graphics, some of the components of 3D graphics and Viewport 3D in particular. But with regards to this camera configurations, WPF, or at least right now, I am actually, if you check out the XAML, I think it's here, yes, I'm utilizing what's known as the perspective camera. And the perspective camera quite simply means that points, or should I say edges of, if we take this cube for example, let's use this as an example, be easier to visualize, and you observe the edges. It's quite hard to see here, I can appreciate, but this top left edge here and this right left top edge here, they all go towards what's known as the vanishing point. And that's what creates this kind of perspective angle of the cube. It's not parallel, these two lines are not exactly parallel to each other because they actually converge at the vanishing point, which would be somewhere in the horizon. However, if you go to the orthographic camera configuration, what would tend to happen, and I don't know if Viewport 3D actually supports orthographic, I'm going to see, but I think it probably does if it supports a perspective. Let me see if it does that. Let me just... It does actually. That's really interesting. I haven't really explored this camera configuration, but with the orthographic camera, what you'll notice is that that lines actually perpetuate indefinitely. They are in a parallel configuration, in a sort of isometric style of view. So again, there's a nice link in MSDN, there's a nice article rather in MSDN, which I will link to in the description, which actually just briefly explains some of this stuff. So I'm going to leave that there for your further reading. This is just going to kind of gloss over some of the basics here. Now, once you've established the camera, the next thing you probably want to do, if we go down, is you want to add some components to your scene. Excuse me. So I have here Viewport 3D children, and within this tag, within this this scope, what I have is model visual 3D, which you can see here. And the model visual 3D class is used to generate renders for 3D geometry. Compositions of objects can be created actually using the model 3D group class, which is another class if you want to make a composite of different renders, different models. You can use the model 3D group class. Now this is where things start taking a little bit more form when we start defining these properties: position, triangle indices, and optionally texture coordinates. And there's also normals, which we're going to go into. So what is positions? What are these numbers? So basically, positions is a property that's used to effectively store the vertex data of the geometry. And I will just simply gloss over a little bit later, after I just go over some of these other properties, what exactly is vertices and indexes. But for now, just know that this positions property actually pertains to vertex information of our render. Now, triangle indices. Because once we have an array of vertices, we need to then tell the program how these vertices are connected. Because right now, these vertices are just simply like points in space. You know, you have this corner, the right-hand top corner, bottom right, left-hand corner. But how do we connect these dots, so to speak, in order to create the shapes that we want? That's where indices come in. They define the way that the vertex information is connected. And I'm going to go through that with some more graphics so you can more visually see what's going on, but I'm just going to briefly introduce it to you. It's actually quite useful for us to know that in certain lower level 3D graphic programming layers, there is a way to define the kinds of primitive geometry that we want to render. So, for example, with DirectX, the enumerator type primitive topology is a list of preset primitive types such as triangles, triangle list, etc. And this way, when we define from the primitive topology enumerated list the kind of geometry we want to specify, the program can then know that, as in the case of Viewport 3D, that or should I say in the case of DirectX, every 3 vertexes in the case of a primitive topology type such as, I don't know, let's just say, I think triangle list is one. Just to give you a bit of a context, once we define, say, 0, 0, 0, 10, 0, 0, 0, 10, 0, and 10, 10, 0 for our vertex information, what the primitive topology will say for the triangle list would be, okay, every 3 points constitutes as 3 points of a triangle, and then these triangles are connected with each other, hence triangle list. So then that gives us a little bit of context. Our primitive topology, once we select from that enumerated list, it gives the context to the program as to what kind of geometry we want to form. Again, there will be links in the description if you want to read up on this. This is just a gentle introduction, rather. Okay, excuse me. So without much further ado, let's get straight into before we go into a little bit more perhaps into what's going on here in the XAML, I want to just go a little bit deeper with regards to what's actually going on under the hood and the concepts behind rendering 3D with particular reference to Viewport 3D. So, Viewport 3D WPF, 3D basics. Vertices are the corners where the lines of the polygon meet. So in this very simple example, I have here vertices 0, 1, 2, and 3. And it's worth noting that in the realms of WPF, the origin, if you can see the mouse pointer, it's somewhat at the middle. Traditionally, within the realms of mathematics, the origin is centered at the center of the graph. But in terms of WPF, it actually begins at the top left. So this would be the origin with the x-axis going away towards the right and the y-axis increasing by going down. So not up, not across and up. In terms of a traditional graph, you would expect the x-axis to perpetuate going to the right as increasing and going up increasing. In the realms of WPF, it's actually somewhat the opposite in the fact that you start on the top left corner of the screen and you're going, x-axis is going to the right as you'd expect, but it goes down for the y-axis increasing and it goes up decreasing. So we can examine this concept within 3D geometry also. The mesh geometry 3D class within Viewport 3D supports the positions property as we went through briefly, which defines vertex information for geometric shapes. And there's a little snippet here. So by supplying vertex information, we can generate simple geometric primitives. So as I explained before regarding index arrays, if we consider the example of an unfolded cube object, the program could be made to render all the vertices of the geometry, but do all the vertices need to be drawn and redrawn? Because think about, if we just think about the fact that if we have somewhat of an unfolded cube and we have 3, 4, 5, 6 squares and all these squares are somewhere adjacent to each other, do we exactly need to draw the line here twice for this square here on the farthest right, this square in the middle, and this left square sharing the same face, or should I say the same vertices as the square in the middle? Do we need to render fully 3 squares for the viewer at their perspective to have enough visual information to understand that they are looking at this piece of geometry? Well, that's where utilizing indices may come in handy. So as I briefly touched on, lower level programming layers may allow for definition of geometric primitives that interpolate an array of data in order to represent a desired shape. So the code snippet from above that we observed with regards to the positions described vertex information, but without much of a context, how will we know the kind of geometry we want to create? This is why in the case of DirectX API, the enumerated list primitive topology contains a list of primitive types that describe different geometric structures such as line list, triangle, triangle list, etc. Within the primitive topology enumerated list, we could select, for example, D3D11 primitive topology triangle list, which simply means that every 3n vertex will generate a triangle. Within Viewport 3D, the triangle indices property, excuse me, my screen just went black. For some reason, I don't know if you saw that on OBS side. But anyway, within Viewport 3D, the triangle indices property is an index array that similarly defines the vertices that should be connected in order to form the geometry. Although no explicit primitive topology type classes, so I'm going to just gloss over this because we have gone over triangle indices actually, but in order for, just to explain how exactly the semantics works just a little bit, just very briefly, what is going on here is that since we have our vertex array, these numbers represent the index of the vertexes that we have defined. So this is basically saying at the 0th, or should I say the 0 indexed vertices, the 2 indexed vertices and the 1st indexed vertices are all connected as one triangle. From 0 to 2 to 1, then 1 to 2 to 3, 0 to 4 to 2, so on and so forth, until we have the geometry that we desire. Normals or data also kept in vector 3 arrays, which describe the way that light hits the surface of the geometry. So normals are somewhat optional in the sense that in Viewport 3D, you can omit the normals property from your geometric code base. However, it will be inferred within the positions under the hood. I think it will be defaulted to a particular value. I'll leave a link if I can find the right article that describes this perfectly in MSDN. Otherwise, yes, normals can be defined, and they just basically describe the way that light hits the surface of the geometry. So this actually more or less brings us to the end of the video. This is just a gentle introduction to some of the concepts behind Viewport 3D, how the semantics work, and in subsequent videos, I'm going to be going a little bit deeper into forming more complex scenes. I want to see what I can do with regards to textures. And maybe if I can figure out some more advanced rendering techniques. And I have a project, a rough project I have with a 3D rendering framework using Viewport 3D with some C# backend to help with the rendering. So not everything has to be scripted by hand, as you see in XAML. The disadvantage of using XAML is that everything has to be scripted by hand, but it's also a good learning experience if you are starting out this kind of thing for the first time. You can visually see what's going on. But using C# can leverage the computational power of the CPU in order for you to not have to do the calculations yourself, and thus you save a lot more time when creating more complex and compelling geometry. So thanks very much for watching this video. I hope you found it somewhat informative. Feel free to hit me up on LinkedIn. I'm William Steady Jimmo on LinkedIn, and check out the channel for more videos like this. See you in the next video. Bye-bye.